Welcome back. Today, we are going to discuss calorimetry, how we measure thermal energy, Q values experimentally. We'll explore calorimeters, exothermic and endothermic reactions, and solve a combustion problem. If you are new to thermodynamics, please watch the previous video on the first law of thermodynamics and come back. Perfect bridge to thermochemistry in action. Let's heat things up. What is a calorimeter? A calorimeter is our lab tool for measuring heat transfer during reactions. It captures Q from the first law. Remember, energy is conserved, just transformed. Key to remember: we measure the change in the surroundings temperature to find the system's Q. Exothermic: heat out, like combustion warming your calorimeter, system Q negative. Endothermic: heat in, like dissolving salts cooling it, system Q positive. First type, coffee cup calorimeter. Cheap, DIY, styrofoam insulates. At constant pressure, the heat measured is exactly delta H. Reaction recall: isobaric system Q equals delta H. Great for aqueous reactions. No volume work complications. For firepower, bomb calorimeter. Sealed bomb at constant volume. Work done is zero, no P delta. So according to the first law of thermodynamics, you can use Q equals delta U directly. Isochoric process. Perfect for combusting fuels explosively. A water bucket absorbs heat. Temperature rise tells all. Connects to delta H approximately delta U plus RT delta equation for gas. Here is a comparison between the coffee cup calorimeter and the bomb calorimeter. Look at the differences. Core principle: system or chemical reaction loses heat and the surroundings, which means the calorimeter gains it. That is the first law of thermodynamics conservation. So, Q reaction equals negative Q calorimeter, that is equal to the negative C heat capacity of the calorimeter times delta T. Heat capacity of the calorimeter, if not calorimeter constant, is fixed, like the effective heat capacity of cup plus water. Calibrate first, then measure. Now, hands-on. Calorimeter problem. Pause a video for 1 minute and try to understand the question. First, calibrate. The heater adds 27.8 kilojoules. Temperature rises 4.88 Celsius. Solve for the heat capacity C of the calorimeter. Q of calorimeter equals C of calorimeter times delta T. So, C of calorimeter equals Q of calorimeter over delta T equals 27.8 over 4.88 equals 5.69 kilojoules per Celsius. This fingerprint is used for unknowns. Pause. What? Next, burn 1.75 grams of methanol in the same calorimeter. So, produce energy in reaction. Q equals energy absorbed by the calorimeter. Q cal delta T equals 6.97 Celsius. This is an exothermic reaction, and the temperature goes up. Q of the reaction equals negative Q of the calorimeter equals negative 5.69 times 6.97 equals negative 39.70 kilojoules. Finally, calculate the molar energy. Number of moles methanol equals 1.75 over 32.04 equals 0.0546 moles. Delta U of the reaction equals negative 39.70 kilojoules over 0.0546 moles equals negative 727 kilojoules per mole. The standard combustion value is negative for exothermic reactions. Summary: calorimetry quantifies the first law in the lab, calibrates, measures delta T, compute Q. Subscribe and stay tuned for new videos.